it's best to illustrate these concepts of what these matrix elements mean and how they can be used with a few examples. And so let's take a look at that. With this first example, here I have the left end of a long plastic rod. The refractive index 1.56 has a convex spherical surface of radius 2.8 centimeters. An object is 2 millimeters tall, is placed in air on the axis at a point of distance of 15 centimeters from the plastic, and you need to find the position and size of the image inside the rod. We've actually done this problem early on. And what you find is that if you have in this particular system, the parallel light goes through the secondary focal point, and a light straight through to the center will pass straight through undeflected, and where they intersect gives me the image of this arrow over here, and the way I've got it drawn, it's hard to say precisely at this stage, but the way I have this drawn is that it's a inverted image, and a few finer points. Generally, in these problems that involve finding where an image is cast for a given object, you put the input plane right on the object. This is an object that's an arrow of height 2 millimeters. And you put the output plane, so the input plane is on the object, and the output plane you put that nominally where the image would be. In this case, I don't know where the image is, so I just left that at X. I do know where the object is. It's 15 centimeters above, in front of the interface. I know what the index of refraction is on the object side, and I also know the plastic that extends on indefinitely here is presumed. I know the index of refraction of the plastic as well, and that's on the image side. And again, from the vertex, I just leave this distance as known. In fact, that's one of the things I want to find. I want to find the position of it, so I want to find X. Well, to do that, I have to get the system matrix. And notice here the element is this spherical interface between two dissimilar indices of refraction media. I've got a translation to get to that point. I get from one side to the other of it with a refraction matrix, and then I get another translation. So I need to form the transfer matrix from my input plane all the way to my output plane. And I really have three elements: a translation, a refraction, and then another translation. When I wrote this down, I actually start on this side and get the matrices in reverse order. So I started over here. I'm going to translate by 15 centimeters, and if you go look at that transfer matrix for a translation, it's 1 times the distance of translation 0, 1, and in this case, to go 15 centimeters, I have 15 centimeters up here. Then I have to get from one side to the other of this refractive spherical interface. The general formula is this. N2 is the one that's on the right, N1 is the index of refraction, the one on the left, and R is the radius of curvature. I can fill those in pretty easily as well. N2 was 1.56, N1 was 1. N2 was 1.56, and the radius, we use our sign convention for convex, that's a positive radius, and so R is positive 2.8 centimeters, and then I've got this overall minus sign. And then I have 0 for this element. N1 was 1, that was air, and N2 was 1.56. So I've got these two. That gets me just on the other side of this interface. And then I do another translation, and this time by a distance x, which I need to find, actually. So I just leave that as an unknown. Well, when I calculated these, I got 1, 0. Those are easy. This one here, the C for this particular matrix is minus 0.128, and then 1 over 1.56 was 0.61. And now I'm in a position where I can multiply these out. When I multiply this row times this column, I get 1. This row times this column, I get 15, so that one's easy. This row times this column, I just get this first element. And then the only one that really involves much calculation is this row times this column. But when I did that, I got minus 1.28. Pretty obviously, here's where something like a program like MATLAB, it really excels in multiplying matrices like this. So, and then the final one, so I'm now down to this. So I multiplied these two, got this one. And now I multiply this one times this one. And then I get 1 minus 0.128x. I get 15 times minus 1.28x. And then I get 0 times that is minus 0.18, and 0 times this. I just reproduce this second row. So there's the transfer matrix that takes me from the input to the output plane. Well, this is a case of imaging, and we've already denoted that. Let's see. If I have all the rays coming out of P, and all the rays are going through the single point P prime, that's the image. And in that case, remember that was a case of locating the image point, and that was when B is equal to 0. So to locate the location of the image, I have to have the right x so that this term vanishes. So 15 minus 1.28x. Solve that, I get 11.7 centimeters is x. And then when B vanishes, then the magnification is whatever the value of A is. Well, here's the value of A, but now I'm at the point, now I have to be at the point where the image is cast. Excuse me. Excuse me. The 11.7 is x. And so I know the magnification, h prime over h, is 1 minus 0.28x at the point where the image is, which is at 11.7 centimeters. H prime over h, 2 millimeters, and one then gets h prime, and as advertised, I get it's a reduced image, but it's also inverted. I actually worked this problem with just the matrices, not really knowing whether it was inverted or not. I found that it was inverted, and then I came back and drew this picture just so that it looked like the results that we get. Well, that's the first example. Now, whether you find this easier or not than just doing it the sort of the old-fashioned optical interface way is a matter of taste, I suppose. But ultimately, for very complicated systems, especially ones where you can let a computer do all this this matrix multiplication for you ultimately has sort of won out, and so now there's lots of computer programs that people, optical engineers, use to do these kinds of calculations instead of doing them by hand here.